So the outline for today's presentation is this. And first, Rebecka will tell us a bit about natural language processing, which is a huge field. She will boil it down for us. And then Isac will tell us about the vector representation of words, which is kind of what we're focusing on today. And then I will talk a bit about machine translation. And Rebecka, again, will talk about generating clickbait headlines. And finally, Isac will summarize the presentation. So I give the floor to Rebecka.
So, the topic for today's presentation, natural language processing. Let's talk about what that is. The aim of natural language processing is to create computer systems that can understand and output natural language, but that doesn't really tell us a lot unless we know what natural language is. So what's natural language? Basically, it's language that develops naturally in humans, typically in kids as they grow up. So it's a language that develops without conscious planning, and it's typically learned by use. The opposite of a natural language would be a constructed language, which could be a programming language such as Python, or something like Loppan, which we talked about in the linguistics seminar a couple of weeks ago. So in practice, a natural language basically means that it's the type of language we use to communicate between humans. So it could be English or Swedish or Swahili. Now, what's the point then of natural language processing? It's a significant part of the path to artificial intelligence. So the goal is really to simplify communication between humans and machines. And I'm sure most of you have seen, for instance, old people struggling with technology and how to communicate with it. So the goal here is to simplify that so that we can talk to machines the way that we talk to each other, which comes naturally for us. And this is obviously a huge field, and there's a number of different aspects of it that are being worked on. And here's a few. So we have automatic text summarization, classification, and translation, and those are all concerned with understanding natural language. So not just understanding the words themselves, but also the meaning or the content of text. Then there's text generation and question answering, so that's also concerned with creating or outputting natural language, not just understanding, but also responding in a way that we can understand as natural language. And finally, we have things like speech recognition and sentiment analysis. So here we're trying to understand verbal communication or understand human feelings. So for instance, if a movie review is positive or negative, things like that. And the aspect that we've chosen to focus on is the understanding part, and we're going to talk about a specific algorithm that can be used to train or to learn how to understand natural language. And Isac will tell us more about that.
Okay, so how do you actually teach a machine to understand the meaning of words and the context? I mean, we obviously can't barcode every word and their context, so we need some type of algorithm. And I'm going to talk about one such algorithm, and it's called vector representation of words. And as the name implies, it represents or translates a word into a vector. And the vectors are usually in the dimensions between 50 to 200. And what we want is the distance between the vectors to tell us how the words are related. And I try to illustrate it in the picture here, where we have the projection of 4 words on a plane. So king is very closely related to queen, so the vectors are very close to each other. But king is not as much related to uncle and aunt, so they're farther apart. But all of these words are related through gender, so it makes sense to plot them in the same plane. But how do you actually translate a word into a vector? I mean, that's not very obvious. But we don't really need to know, because we can let our neural network figure it out for us. So to train a neural network, we need 2 large data sets. One containing just words, and one containing contexts or sentences of these words. There are then 2 primary algorithms that I use to train the system. The first one being continuous bag of words method, which can be seen here to the left. It's a bit hard to see. And in this method, you feed the system an incomplete sentence. For example, the dog chases the blank, and the target output is then cat. And in the other method here, so the so-called skip-gram method, you would feed the system only one word, and the target output is then a set of words that are very likely to be in a context of that word. So it's just the other method in reverse. Of course, there are other methods, but these are primarily used because of their speed advantage, because they don't really contain any hidden layers. There's only the projection of the words to the vector space. Yeah, and this has been done by two research groups, one from Google and one from Stanford. Some of you might have heard of their projects. They're called Word2Vec and GLOB, respectively. And the results are very interesting. The system is able to distinguish many similarities, many degrees of similarities between words. So, for example, it is able to identify that king is related to queen through gender. So, by using basic vector operation, we can see that we get that king minus man plus woman equals queen in the system. And similarly, you get that Windows minus Microsoft plus Google plus Android. And you could also ask the system to fill out the sentence, knee is to leg as elbow is to and the three most likely outputs were then forearm, arm, and ulna bone, where at least the two first makes a lot of sense. So yeah, and the system is also able to identify some basic grammars. It's able to identify that. It's able to see that the word dog is similar to the word dogs in the same way that man is similar to men. So yeah, I think that's it for me. So Britta is going to talk about our first application.
Yeah, so let's dive into machine translation. So the basic idea around machine translation is that even in different languages, the simple kind of words describing reality, they relate to each other in quite a similar way. So I hope you can see these pictures, because we have some English words and some numbers and some animals and then Spanish representations. And you can see that the geometrical, they look the same. The point is that the axes, they don't have the same values. I don't think you see that. No, okay. The axes don't have the same values.
Yeah, I was thinking, can you turn off the light?
Yeah, no. Is it? Yeah? Okay, so they don't have the same values, but they kind of look the same. You can see that cat relates to cow in the same way that cat relates to vaca, right? So these pictures were produced using the vector representation that Isac told us about, and then they used the physical component analysis, projected them to 2 dimensions, and then they just rotated them. So this shows us that the words actually relate to each other in a similar way in different languages. And this can be used to translate between languages using a simple linear projection or matrix multiplication. Sorry. And this was done by some of the guys behind the Word2Vec project, Mikolo et al., in 2013. So we're going to have a look at their implementation and some of their results. So this is a 2-step thing, generating the dictionary. First of all, we need to build these vocabularies or word spaces of each of the languages we want to translate in between. So we choose either the continuous bag of words model or the skip-gram model, which Isac told us about. So Mikolo, they chose the continuous bag of words model because it's slightly faster. And after that, you need to find the matrix which transforms between vector spaces, and this is kind of basic linear algebra. And then this makes it possible to translate between the word spaces, but the output isn't the transformed vector. The output is the vector of the target vector space, which is closest to the transformed vector. This means that it's not certain that the translation is actually the translation of the transformed word. Let's look at the maths. Finding the transformation matrix boils down to solving this optimization problem. But the point is that when we solve this optimization problem, we don't actually get the correct translations. What we get is the mapping such that the system or the algorithm thinks that we map each vector onto a vector in the target space. But it's not certain that that's the correct translation, which we shall see. But it kind of works. A way to make it better is to read out some misinterpretations. So we use the cosine similarity as a confidence measure. So what we do in that step is that we just say that, okay, let's transform the word. How close is the closest vector? How good is the interpretation, the translation? Is it good? No, it's really different. So that's just discarded. So after doing these steps, you get some results. And this is some translations from English to Spanish. I don't speak Spanish, and I'm pretty sure some of you guys do. So please be gentle. These are some translations with a confidence score exceeding 0.5. Overall, they're pretty good. Most of them are spot on. We have 3 translations which are not, and 2 of them are ultra and short stuff. It makes sense if we consider the word ultra, I think, to use it in its original form instead of translating it to muy, because, okay, so does anyone here speak Spanish, please? No. Okay, so I can say whatever I want. I think muy means kind of much, which isn't the same word as ultra. I wouldn't use much instead of ultra, actually. So it makes sense to use this, the English word instead of translating it into Spanish. And this,
Spanish, and I agree.
And I think the same goes for the word shortstop, which is the field position, something, baseball. Which, I mean, it's a baseball term. You wouldn't translate a baseball term just as, I mean, most sports terms you don't translate. So that kind of makes sense. And the third example, it's another kind, is translation of prayers. And the dictionary entry is rezo, which actually means I pray. But the computer translation is oración, so that's actually better in the computer translation. And we'll return to this, that sometimes the computer translation is better, because of course this is what we actually want. Sometimes we get some errors in the translations, as I mentioned. So, for example, if we go from Spanish to English, and we want to translate the word imperio, which means empire, we get the 3 best results, or 3 closest vectors, dictatorship, imperialism, and tyranny. And I think this actually tells us more about the opinions of the author of the text used to create the vocabularies than it actually tells us about the English meaning of the word imperio. So I think you also have to consider what text you use when training your algorithm. So finally, as I mentioned, sometimes the computer translation is actually good. So you can use it to correct existing dictionaries. So again, we have a how-to. First step, you translate the number of words, you take their confidence measures, and you compare it not to the output vectors of the target space, or you compare it to the entries of a dictionary. And you keep those with a low confidence measure instead of keeping those with a high confidence measure. Because then you keep those which have little overlap with the dictionary. So you basically, you keep those which, when the algorithm says, I can translate this word better than the dictionary, or at least they don't agree. So you can revise these entries of the dictionary, you can find some errors. And of course, the Word2Vec group did this as well, and they found, they did this on a Czech dictionary and found like 15% of the entries were wrong, and they could revise those instead of revising the whole dictionary. So they saved a lot of work that way. Yeah, so that was all about this. There's lots to read, and it's really interesting. And I will leave the word to Rebecka now. She will tell us about generating clickbait headlines.
So this previous application was about understanding natural language, but as I mentioned in the beginning, another challenge is creating natural language and outputting natural language. So that's what I'll talk about now. And we will look at an application where a neural network was used to auto-generate clickbait headlines. So let's first talk about what clickbait is. And I'm sure that most of you are familiar with the concept of clickbait. You've seen it, but let's define it anyway. So Wikipedia defines clickbait as web content that's aimed at generating advertising revenue and that relies on sensationalist headlines to attract click-throughs and encourage forwarding over online social networks. So clickbait is stuff that's supposed to encourage you to click it, really. And here's an example of something from BuzzFeed. So clickbait headlines are especially suitable for an application like this because they're relatively easy. Generating natural language in general is very hard, so we like to start with something simple. And clickbait is suitable because these headlines are typically short and they use quite simple language, and they all have very similar syntax, which helps a lot. Plus, they're not even always grammatically correct, which also makes it easier because we don't have to train a network that's perfect. So the first step is to train word vectors, like we talked about earlier, but that's not enough. We also need to train a recurrent neural network to actually output the sentences. And let's talk about that network part. So I'm sure most of you have heard of recurrent neural networks, as they were mentioned in our neural networks course. The point of a recurrent neural network is that it has memory. So it can take both previous and current input into account when it decides what output to predict. They're usually trained using backpropagation through time, which is a generalization of ordinary backpropagation, which uses gradient descent. But there's a problem with this method when it comes to natural language, because the contribution to the gradient will decrease exponentially with a time lag between words, which means that a recurrent neural network trained using this method will have difficulty remembering words that were way back in the sentence. So, for example, in a sentence like, I bought an apple, I am eating the blank, a recurrent neural network like this would have trouble remembering that I said apple earlier because that's several words back. So there's a solution to this, and it's called the long short-term memory unit. So basically it means that we replace the neurons in the network that were previously just simple weighted summarization functions and some activation function with something much more complex, which we'll not go into the details of. But basically these LSTM units, they can learn when to remember previous input and when to discard it. So they can learn what words are important to remember and which are not. So let's look at the actual network used to train this clickbait generating application. When we're training a network like this, we need input data. So in this case, 2 million headlines were used from all of these websites. And it also used pre-trained word vector representations. So that's basically to save some training time. You can start from something that's already been trained. So in this case, the word vectors had been trained on 6 billion tokens from Wikipedia, which means that even at the start of training, this network has some sense of how words relate to each other, like the king and queen and woman thing that Isac mentioned earlier. And what we're going to do is basically train a little bit more specifically on these headlines. So the network used for this application was a recurrent neural network with 2 recurrent LSTM layers, and the word vectors in this case were 200 dimensional, which is a lot. Now let's look at some of the output. So here are some headlines that were generated by this network. And overall, I think they're pretty impressive. Most of them are grammatically correct, and a lot of them make sense. Some are less likely to appear in the real world, but they do at least make sense. I would click a lot of these. And they're also interesting because they show that the network has some kind of grasp of how things relate in the real world. So a good example is the first one, which says John McCain warns Supreme Court to stand up for birth control reform. John McCain probably wouldn't say that, but he is likely to say something about the Supreme Court. He is likely to have an opinion on some birth control reform. So the network has understood these important concepts, and it strings together a headline which kind of makes sense, even though it's not likely to be real. Another example is the one that says Mary J. Williams on coming out as a woman. So when you see this headline, you might suspect that there's something in the training data set about coming out as a woman, and there is, but the closest we get is former Marine Chronicles' journey to coming out as a trans woman on YouTube, which is not really the same. So the network was able to extract the important part, which is coming out as a woman, and it's added a completely different name, which is Mary J. Williams, and that name does not occur in the data set. So here the network has come up with a name entirely on its own by stringing together parts of names, and it's understood that Mary J. Williams is the kind of name that might come out as a woman. And finally, we can look at Romney camp. I think you are a bad president. So Romney camp does occur in the data set quite a few times, but here the network has understood that Romney camp is likely to criticize the president rather than say, you know, he's great, which is interesting. And to further prove that the network can understand relations in the real world, we can ask it to complete sentences. So we'll start with Barack Obama says. So here are 3 outputs. Barack Obama says it's wrong to talk about Iraq. Barack Obama says the GOP needs a new immigration policy, and Barack Obama says he's wrong. So Barack Obama probably wouldn't say in public that he's wrong, but he probably wouldn't say that it's wrong to talk about Iraq either, but he is likely to say something about Iraq. And the second one is spot on. That's something he actually might say. So here the network shows that it's understood that Barack Obama is a politician. He's likely to say something about Iraq or the GOP or an immigration policy. Whereas if we instead start from Kim Kardashian says, we get a completely different output. So here we instead get Kim Kardashian says Kanye West needs a break from her, or Kim Kardashian says she's fake, or Kim Kardashian says she's married with a baby in the next room. So, but now it's understood that Kim Kardashian is not a politician. She's not going to say anything about Iraq or the GOP or a birth control reform. She's much more likely to say something about Kanye West or looking fake or a baby. So it just shows that this network is actually really good at grasping real world concepts. And that's what I had to say about these clickbait headlines. And I'll turn it over to Isac to summarize what we've talked about today.
Okay, so Rebecka began the presentation by giving a brief introduction to natural language processing and why it's important to improve the language processing of AIs. I then introduced us to vector representation of words as an algorithm to achieve this, and I talked about how you train a neural network to obtain the word space that we need. Britta then talked about the first application, which was the automatic translation or machine translation, and she discussed the benefits and disadvantages of this method. Finally, Rebecka talked about automatic generation of clickbait, and she also mentioned a modified recurrent neural network as a way to give the system a longer short-term memory, which is very useful when creating longer sentences. Yeah. That's it for us. If you're interested in reading more about this, I think you should check out the GLOV and Word to Vector project. Are there any questions? If not, thanks for listening.
So great. So